Hi guys, in this video we will look at substitution of leaving groups on aromatic rings. When I say leaving groups, I'm talking about traditional leaving groups such as we saw with substitution and elimination reactions. And the most common leaving groups there were your halogens. But we also had other leaving groups such as an OH group. Of course, you had to protonate that to make it a better leaving group. So your traditional leaving groups. Now in the EAS mechanism, the H is leaving, it's being replaced, but it doesn't leave and take electrons with it. It doesn't become H minus. And so it's not a traditional leaving group in the context of our substitution elimination reactions that of course can occur at a tetrahedral carbon. So again, the most common is halogen. And look at this substrate here. We have a chlorine. And if you take this molecule, 2-chloronitrobenzene, and treat it with sodium ethoxide, this oxygen anion, which can be a nucleophile, we see that the ethoxide can replace or substitute the chlorine on the aromatic ring. So it is a substitution reaction. But as we'll see, it's not SN1 or SN2 because you don't do those mechanisms on a sp2 trigonoplanar carbon. Those mechanisms are only done on tetrahedral sp3 carbons. So this is a new substitution mechanism. Now, by the way, if you try to do the same reaction with 2-chloroanisole or orthochloroanisole, same conditions, no reaction. The nucleophile will not substitute the chlorine. Clearly, the nitro group is playing some beneficial effect here, yeah? Or the methoxy is playing a detrimental effect. Now, we will see that if you do this reaction here, but at much harsher conditions, and here like 300 degrees, sometimes even with pressure applied, we can get a substitution reaction. But very interestingly, the nucleophile can end up where the leaving group was, but also somehow it can end up next door. Thus, these would be constitutional isomers. How can that happen? Why did it not happen up here? Okay. Ultimately, there are two different mechanisms where we can do substitution of a traditional leaving group, and they are called either nucleophilic aromatic substitution, nucleophilic, not electrophilic, not EAS, but NAS. Here the ring reacts with a nucleophile, and we do a substitution. But again, in EAS we're substituting an H. In NAS we're substituting a more traditional leaving group. We can also substitute leaving groups by a benzyne mechanism. Here's some questions to consider. Okay? We will begin by looking at the NAS mechanism. This shows a general overview. Aromatic ring with a leaving group, some type of nucleophile. Nucleophile replaces the leaving group. If this is the nucleophile, the ring must be an electrophile now. As I mentioned, the mechanism is not SN2 because backside attack is impossible. Okay, backside you'd have to come in through this ring. But more importantly, if we were to have a nucleophile come in here and add to this carbon, the pi bond would be broken the weaker pi bond would be broken before the stronger sigma bond to the leaving group. So you're just not going to do an SN2 here to get to this product. It's also not SN1, which would involve leaving group leaving, yeah, to form a carbocation. That's not going to happen because this carbocation is very unstable. It is not resonance stabilized. And I know most beginning students look at this and say, oh, it looks resonance stabilized, but it is not. You need to understand why. All right, if you understand resonance and structure here, you will recognize it is not a delocalized carbocation. Well, the mechanism is also not EAS, of course, because the ring is reacting with a nucleophile. In EAS, we react with electrophiles. Of course, EAS typically replaces an H. There are some specialized cases where an EAS could replace something other than an H, but it's not EAS. The mechanism is either NAS or benzyne, as we mentioned. Let's look at NAS. Okay? All right. Now let me redraw this starting material with the pi bonds drawn in very precisely. All right. And we're looking to replace or substitute the chlorine with the methoxy in this case and produce Cl minus, leaving group. All right, we have methoxy, methoxide. All right, this is ionic, right? How can we show a mechanism? Well, we don't want to have the chlorine just leave. We said no up here. About the only thing you can do here is these electrons come in. By the way, why would they be attracted there? Well, we have a dipole. Chlorine is electronegative. Same as this. Why would a nucleophile such as a methoxy be attracted to this carbon? Okay. Well, we have a dipole there, right? But that's SN2. Nucleophile N, pi bond broken. Over here, nucleophile N, as we said before, we're not going to break the stronger sigma bond. I'm sorry, over there I said pi bond broken. Sigma bond broken. We break the weaker bond, and the weaker bond is the pi bond. We move that away from the carbon. Either one of these lines can be the pi bond. I'm going to have this be the pi bond and move it onto this carbon. And that's going to give lone pair here, and that's a minus charge. That carbon, of course, has a hydrogen there. And we call this nucleophilic addition. Now, note that this is this, which we can call a sigma complex. Okay? But it is negatively charged. In EAS, the sigma complex is positively charged. Look back at that. Now this sigma complex is resonance stabilized. And we will show resonance structures. Need to be able to show resonance structures of intermediates in these mechanisms. These electrons can move here. These electrons move out, and we get pi bond here, here, These electrons move in here and these move out. Lone pairs, of course, and that's it. And of course the resonance hybrid, if we were to draw that, we have bond and a half here, bond and a half here, bond and a half here, bond and a half there, and we have partial minus here, here, and here. Sometimes folks will show just a partial minus all through here, because really once we start doing resonance, really MO takes over, but usually we stick to atomic orbital considerations at this level. Okay, we see that this carbon here is tetrahedral and it's not fully dilocalized. Okay, there's no p orbital there. So the intermediate is not aromatic. It's charged, so it's a high energy intermediate, higher than the starting. All right. So when this comes in, nucleophilic addition, it gives that, right? Of course, none of these structures are the real structure. The true structure that's formed upon nucleophilic addition of the methoxide is this intermediate right here, right? That's the resonance discussion. But it's hard to work with these partial bonds. All right. Next step. There's only one next step. And that is for the electrons to come back in. I'm going to do a different pin. All right. We can work with any resonance structure. None of them are actually real. Okay. In real life, I'm working with this, but it's hard to work with. Next step is the electrons come back in and reform the pi bond, but they kick off the better leaving group. And the chloride would be a better leaving group than the methoxide because it's more stable. And when we kick it off, we get our product plus Cl minus. Now, of course, we could have used any resonance structure. I could have come over here and did this here and kicked it off here. Either way. Now here I would have to use two arrows. These electrons here and these electrons here and kick it off, but it's more direct using either one of these. Okay, and what did we just do there? We did an elimination. We eliminated the chloride. We reformed the pi bond and eliminated the chloride leaving group. Now overall the mechanism was two steps, an addition followed by an elimination. And NAS is sometimes just referred to those two steps, an addition elimination mechanism. We've also did something like this in one of our very first lectures when we were working with thionyl-chloride and tosyl chloride, if you want to look back at that. All right? We break the weaker pi bond here. Again, because it's an sp2 carbon. If it was sp3, we would come in here and we would break the stronger sigma bond at the same time. So it's an addition, elimination, substitution mechanism. Now, guess what? This reaction, as I just showed here, I have to tell you, does not work. This reaction does not take place with mild heat. Okay? Does not happen. If you take chlorobenzene and stir it at room temperature with sodium methoxide in some inert solvent, this reaction will not happen. What does that tell us? First of all, why did I show it if it doesn't happen? Well, let me explain. But what does the fact that it does not happen tell us? It tells us that there must not be enough energy to overcome the activation energy of the rate determining step. By the way, if we draw a reaction coordinate diagram, right, we have A, we have B, and we have C. A, B would be higher, and then C. I'm not going to try to distinguish between A and C. They're both pretty similar. They both have sigma bonds. I'm just going to draw it pretty close. We could get out our calculator. It's probably exothermic, but it's very close. It's hard to tell by just inspection. It doesn't matter. All right, and we go boom, form our resonance delocalized anion, and then we would expect the next step. All right, that is our activation energy, rate determining step. Next step is expelling that leaving group. Anytime you make a pi bond and kick off a leaving group, that's pretty easy. Not going to take much activation energy, just a little, and we get back to the energy level of product. All right. The reason this reaction doesn't happen, we must say, is apparently it's too high in energy. The intermediate is too high in energy. And at room temperature, with mild heat, there's not enough heat to get us over this hump, right? That's why the reaction would not take place. So, can any NAS mechanism take place? Can this mechanism take place at any time? Yes. We need to lower the energy of the intermediate. Well, it's already resonance stabilized. You would think, well, it looks kind of stable to me. Apparently not. It doesn't happen. Apparently it's too high in energy. How can we stabilize this intermediate further? Well, here is one way. We can modify the starting material to give us even more resonance structures. That would stabilize the intermediate. And we can do that. Stick with me here. What if we add a ketone at this position? Like a methyl ketone. All right. All right, I'll put it up here as well. Ortho to the chlorine. Would that help us in any way? And the answer is yes, because right here, we would get an additional resonance structure. These electrons, okay, if we go this way, I'll call that A. But if we come this way, electrons here, and move this pi bond out onto oxygen, and I'll call that B, we would get an additional resonance structure. Please pause the video and draw it. You can always be doing that and work ahead of me. Okay, that would put a third lone pair on this oxygen and minus on oxygen. Now we have 4 resonance structures, even more delocalization, but more importantly, we have delocalized the negative charge onto a more electronegative atom. Up here, the charge is delocalized onto 3 different carbons. Now it's delocalized to oxygen, and that is a very stabilizing effect. All right. So now the intermediate is much lower than before, all right? And I'm just going to put it maybe here. This is going to be the B with what? Well, it's with ketone, with electron withdrawing group, ortho or para to leaving group. Now in the example I showed it ortho. That's going to lower the transition state energy of the intermediate, okay, or it will have a lower transition state. And now it will be much easier to do this reaction. And now we know that it will occur at much milder conditions, under much milder conditions with lower heat. It will occur at room temperature. If we have a group that the negative charge can be delocalized into, and the negative charge ends up on a more electronegative atom than carbon. Now, groups have to be ortho or para, because look, that's where the negative falls. Ortho, see, that's also ortho to the leaving group, or para. I could have put the ketone group, the carbonyl group, ortho or para. The negative charge never falls on the meta position compared to where the leaving group is. So if I place the ketone group or the electron withdrawing group there, I would not have been able to draw the additional resonance structure. All right, so what's the requirement for an NAS? Right here. We need a strong, I'm going to say strong, electron withdrawing group, ortho para to the leaving group. What are examples of strong? Okay, carbonyls, but also nitro groups. Basically the group 4 in the EAS. Sulfones, sulfonic acid groups, carbonyl groups, nitro groups. Those are the most common to facilitate the NAS. What is the rate determining step? Well, it's the nucleophilic addition. Okay. Right? What type of leaving groups work in an EAS? Well, first off, leaving group ability is much less important or much less strict than with SN1, SN2. Okay? With SN1, SN2, we say the halogens are good leaving groups, with iodine being the best. We also say oxygen if we protonate it. Okay, tosylates are good leaving groups. There's a few others, maybe a positive nitrogen sometimes. In the NAS mechanism, many things can serve as leaving groups because, all right, the leaving group leaves in the fast step, right? The rate determining step, the leaving group hasn't left. Okay? The elimination is the fast step. Loss of the leaving group is fast. It means it's easy. And so we don't have to be as strict about what type of leaving groups can leave here. If you've ever seen it be a minus, it can probably leave in an NAS mechanism. Now also, your trend for your halogens is opposite here. In NAS, the fluorine is actually the better leaving group. Because, what do we mean by better leaving group? That is, the fluorine makes the reaction faster. This substrate would be faster than this one. That means the leaving group is better. But why? It's not because the F is just a better leaving group. We don't need to talk about the leaving group ability of the F. We need to talk about the rate determining step. The rate determining step is the nucleophile attacking that carbon. Well, guess what? The CF bond is more polar. There's a stronger dipole here. The F is more electronegative. Okay, and there's more partial positive on that carbon than this carbon. And since there's more partial positive there, the nucleophile will be more attracted there, and that will help make the nucleophilic addition easier. Essentially, it lowers the activation energy. Because when you got stronger charges attracting, that's more favorable, it's easier, it's going to happen easier. So we say, yeah, the F is a better leaving group, but it's not because it's actually leaving. It's a better leaving group because it imparts a stronger partial positive on the carbon it's bonded to. All right? Now in SN1, SN2, the leaving group leaves in the rate determining step. If you look back at those mechanisms, you should know that anyhow, right? But not in an NAS, leaves in the fast step. All right, let's look at some examples of NAS. If you take this compound here, and by the way, since fluorine is the best leaving group, you often see NAS reactions with a fluorine. It has a nitro group, ortho or para. All right. By the way, terminology. Back over here. Does it now make sense why this undergoes an NAS, but this one does not? All right. Strong electron withdrawing group, ortho para to leaving group. And you should draw out the nitro group. You should be able to draw resonance structures, just like we did with the ketone, into the nitro group. All right. But here, the methoxy is not a strong electron withdrawing group. It's actually a donating group. A donating group is not going to stabilize the anion that is formed in the intermediate. But some important terminology. Is it okay to say that the nitro group activates the substrate for NAS? I mean, right? If it wasn't for the nitro group, it wouldn't happen, so we can say the nitro group activates this molecule for NAS. And you will hear that terminology. But then students will get confused and say, but I thought nitro group was a deactivator. Yes, it is. For an EAS reaction. But it is actually a activator for a NAS reaction. It's just the opposite. The electronic trends for substituents with EAS are just the opposite for NAS because NAS involves an anion intermediate and not a cation intermediate. The ketone group here activated chlorobenzene for the NAS. Of course, this is called, what, 2-chloroacetophenone? All right, so be aware of that terminology. Don't be confused by it. Okay, we see here, of course, we have Na plus and we have SH minus. It's analogous to hydroxide, except it's SH. Good nucleophile, and we displace the F by a NAS mechanism. You can practice your mechanism. Showing the nitro group, okay, resonance there. Take this substrate, multiple substituents with ammonia. Ammonia can be a good nucleophile. And it displaces the chlorine here. Why? Well, it is the better leaving group for NAS, but that's not the reason. Only the chlorine has a strong electron withdrawing group, and by the way, a cyano group would also be a strong electron withdrawing group, group 4 in the EAS discussion. Only the chlorine leaving group has a strong electron withdrawing group, ortho or para. It actually has one both. So both of these groups is going to be kind of doubly activated for NAS, where the bromine does not have a strong electron withdrawing group, ortho or para. So we'd only expect the chlorine to be substituted. We need to lose an H from the ammonia, and as a very last step, the Cl minus leaving group can take that H, and we would produce HCl. Now that could be a problem because the ammonia could react with the HCl. We may want to include a base in this reaction to quench the HCl that could theoretically be formed. I'm leaving that out. Okay, I'll leave the next two for you to do for homework. Think about those. All right. Please show mechanism for the top. Practice your mechanism, drawing resonance structures into the nitro group. Just like we did here, except here I had a ketone group. Okay, that is your NAS mechanism. I think there's an application here, the synthesis of olanzapine, an antipsychotic type drug. By the way, this is some of my favorite chemistry, analogous to research. It's a great multi-component reaction here to make this aminothiophenone. But at this step, there's an NAS, and they're bringing in here this orthofluoronitrobenzene, and it looks like the amine here, the amino group, is displacing the fluorine. Well, the fluorine has a strong electron withdrawing group, ortho or para. This looks like a classical NAS mechanism. The sodium hydride probably deprotonates this and makes it a nitrogen anion first, because it's a fairly weak nucleophile because it's so delocalized. THF is the solvent, but it is an example there of an NAS. They follow that by nitro reduction using tin 2-chloride. That is possible because the tin 2 gets oxidized to tin 4 in the reaction, while the nitro group gets reduced. Now, once it gets reduced, it attacks the cyano group, and so they're not showing just the amine here. They actually, down below, when they do a similar reaction sequence, they do this similar NAS first, then they reduce the nitro group with hydrogenation, And you see that it just shows the amino. Then only later do they come in and make the 7-membered ring. Okay, so up top they sort of make the 7-membered ring sort of all in one step here. They do it a little bit differently down here. So 2 different nitro reductions there. Where early on the nitro was your activating group for your NAS mechanism. And note that they use the F because that's a better leaving group than maybe a chlorine or bromine. So a little bit of application. Okay, in the next video we will look at the benzene mechanism.